All right, so welcome back everybody for the first in-person session of the Cardiff Analysis Seminar of this calendar year. Today we're delighted to have here in the flesh Hinz from Bielefeld University.
Hi everyone.
We'll talk about boundary value problems on non-Lipschitz uniform domains, stability, compactness, and the existence of optimal shapes. So it's very promising, so thank you very much.
Thank you.
The floor is yours. Yeah.
Can I take it? Yes. Hello everyone. Thank you very much for having me here. It's a great pleasure to be in Cardiff. Actually, I'm around relatively frequently here in Wales, but due to COVID and many other practical circumstances, I never managed to pop by. But now I'm very grateful that we can meet in person. So the thing I would like to talk about today is boundary value problems, and it's basically about a project I did with two friends about existence of optimal shapes. So how does it go? It doesn't work? No? Something wrong? Now it works. Thank you very much. So the goal is we will look at some equations, and we would like to find optimal shapes. By optimal, I mean energy minimizing shapes. So we will look at more or less the same type of energy functional, but we will change the domains and then ask which sort of domain makes this energy minimal. And the point is we will encounter a situation where if we try to look at smooth domains or Lipschitz domains, then this is not so obvious how to do it for these boundary conditions that we will impose. It has not been known formally that there's some sort of compactness so that you can prove the existence of a minimizer. So what we will do is we will relax the regularity assumptions on the domains quite drastically and allow very rough, irregular domains with possibly fractal boundaries so that we have a very rich, large class of domains to choose from, and then we can observe compactness. So first I will talk about motivation a little bit, then about traces, extensions, and well-postedness, which is probably a little bit boring for some. Please speed me up if it's too boring, right? Please just speed me up. Then I will come to some results on convergence and stability, which are more interesting, I guess. And then finally talk about compactness and existence of optimal shapes. So these results are together with Anna Rosanna Vapiera from Paris-Saclay and Sasha Depliayev from University of Connecticut, two very nice people. I love them very much, two friends of mine, and I learn a lot from them. So let's see. Okay, so first practical question, which is not exactly at the core of what I will be talking about today, but where the sort of the motivation comes from is acoustics. So one practical question is how to optimally reflect or absorb sound waves. And you see some picture here. So this is Elbphilharmonie Hamburg. So it's a fancy concert hall, and this is really the concert hall from inside. And you see it has a quite interesting architecture. And this interesting architecture is well calculated in some ways, at least. So that you can absorb some frequencies, for instance, the noise of people sneezing and so on, and can enhance other frequencies, so the different instruments, the orchestra, in particular spots. And so this is quite well balanced. And there's not only this macro structure in this architecture, but also some sort of microstructure. So you see here you have little bumps on the wall. So this is a picture taken from a wall, and you have little bumps which are obstacles of a certain size, and then you have these other structures, it's like, I don't know, fish scale-like structures, which are obstacles of smaller size. And this contributes to absorption of sound of certain frequencies. Two other examples where we can talk about, I mean, for today we will focus on absorption, not so much on reflection or enhancement. And two other examples where absorption plays a huge role is aircraft engines. So I didn't know it before, but then from some friends also here in the UK, I learned that actually when you have a jet engine, then there is this piece before the fan that comes where the air enters. And actually there are very tiny little engravings here. Usually one cannot see them nicely. Also, one can almost not see them on this picture. But now when I travel, I pay more attention when boarding and try to see them. And actually the stream of air enters so rapidly that these very tiny engravings already drastically change the sound properties. And people tried, and this principle is called aircraft liners. So, and they try to manufacture these liners in a way that makes the jet engine, I mean, to suppress the noise of the jet engine, to make it, I mean, quieter, which is, of course, in business a very important fact. And the interesting thing is that these engravings that they use, or little bumps that they use, apart from being very tiny, they have tendency to be quite sort of irregular. They have strange geometry, which you would not suspect. I mean, it's nothing obvious. It's really calculated in some way. Here's some other picture. This is Apple's anechoic chamber, where they tested the acoustical properties of iPhone and so on. And this is supposed to be the quietest place on Earth, the quietest room on Earth. Yeah. And also you see many obstacles to sound to achieve optimal absorption. Here is another construction, and actually this goes close to our French friends already. It's a patent, and actually in France at Paris-Saclay and at École Polytechnique and so on, there were many people working in optimal absorption of sound on some sort of experimental and numerical level. And this story, I think, dates back to the 80s at least. Yeah, it goes back to the 80s at least. There was Sapowal, Filoshev, Krebenkov, and so on. So they're still fiercely working on this from applied math side, from physics side, from engineering side. And there's one patent that they have issued for an absorbing wall. So they constructed some sort of absorbing wall, which can help you to sort of make roads or train lines quieter. And they constructed it, they calculated it and constructed it with a very strange geometry. Also here you see you have quite sort of irregular structure. You have these holes, you have these little bumps, and actually this is just very, I mean, it's just shape you can manufacture easily. If you go to numerics, and you look what would be even more optimal, you would find that it would be more optimal to have more obstacles, also of smaller sizes, and so on, right? But at some point, you want to have something that can be constructed. So this is one of the outcomes of this research. And let me start here. If we come from acoustics, then we could look at wave equation, then do some separation of variables, look at single frequencies, omega, and arrive at this type of problem, which is a Helmholtz mixed boundary value problem for Helmholtz equation. So you have quite simple Poisson type equation on the inside of a domain. So the blue one is a domain here. And you look at this relatively simple equation inside. And then you decompose your boundary into different parts. So maybe there is some boundary where you have Dirichlet boundary condition, which for instance could be a noise source, there could be speaker. And then you have other boundary parts that are just reflecting, so they are just Neumann conditions. And then there's a part of the boundary which you can actually vary, and the question will be how to choose it to minimize the acoustical energy. And on this boundary part, you impose Robin type conditions. And Robin type conditions are actually what is what you need to model absorption or partial absorption. Yeah. So we have three types of boundary conditions. The Dirichlet part, the Neumann parts, they are rigid, they don't move, and the Robin part now is allowed to move, because this is where your absorbing wall, in a sense, is supposed to be constructed. Yeah? So speaker, reflection, and hopefully absorption. So this comes from practice. This could be one of these chambers or one of these walls in a specific implementation. Omega, that we just saw, is the single frequency, and then we get some solution U. And of course, if I change the domain, then I get a different solution. So U depends on the choice of omega, and basically on the choice of gamma, because gamma is the part of the boundary that can be varied, right? So for each choice of gamma, we get different omega and different solution U. We will see this is well posed. I didn't say it well posed, but it will be well posed in this setup. Alpha is a specific complex parameter, which is about the absorption properties of the material. F is a domain source, so the domain noise source. So let me go back. I apologize for not having it on one slide. There could also be a chattering crowd in the blue domain. This would be some noise source inside the domain. Yeah. So we have a speaker, and maybe in a train station or airport with a speaker, and we have a chattering crowd inside. All right, so this I told you already. The goal now is to find gamma, so the variable part of the boundary, and therefore to find omega, such that, suppose that omega is recruited from some reasonable class, we can minimize the acoustical energy, which is a thing like that. The acoustical energy over that class. So we want to make this energy minimal. So the energy will, of course, depend on the choice of the domain. And first of all, directly by the norms and so on, but also indirectly because the solution will depend on the choice of the domain, right? And so this is, I just keep it that way because it's merely an introduction now. Yeah. So we want to minimize that energy. So the mathematical problem could also come from some other background, but the main background that we are interested in is acoustics. Yeah. Now, how to talk about this? If we want to do some optimization, then probably it's most reasonable to go to variational approach. So we will talk about variational weak solutions, basically. And if we hope to find some optimal domain, then somehow we should better be able to talk about convergence of such domains and about somehow some sort of continuity properties of the energy functional depending on the domain, right? So that we can talk about minimizing sequences and maybe the limit of minimizing sequences and so on. So the proof of existence of optimal omega typically involves various convergences. First of all, convergences of sequences of domains to a target domain. But also somehow we must talk about the boundary, because the Robin condition, if we implement it in a variational setup, it will talk about integrals on the boundary. So there will be some integrals on the boundary. So we have to think about what should be reasonable convergence for the boundary, for the moving boundary pieces, which are for the approximating domains gamma n, and for the target domain, which we hope to be the optimal one, gamma. A natural tool for this convergence would be perhaps weak convergence of measures on the domains, because I mean, this is something that is, you have good compactness properties, you can easily work with, it's very nice in analysis. So we could try to endow these approximating variable parts of the boundaries gamma n with measures mu n, whose support is gamma n respectively, and hope that these measures converge to some target measure mu, whose support will be gamma. And this is the situation that we would like to deal with, because this is what, I mean, a pragmatic approach to the problem suggests. Now, I would like to stress that if we would impose only Dirichlet conditions everywhere, or only homogeneous Neumann conditions, then we would not have to talk about these measures at all, because we can just abuse Gauss-Green formula, write everything with terms inside the domain, so to speak, yeah, and forget about these problems of measures on the boundary. This is why so one can proceed differently in these cases. And for these, in that respect, more simple boundary conditions, this problem of existence of optimal shapes had already been solved by different people in different contexts. So for instance, in Lipschitz context, in a context connected to BV functions and so on. Yeah. So for different pools of admissible domains, we can find optimal ones to minimize in the sense of minimizing the energy. Yeah. But for the Robin problem, which is interesting for acoustics and which is needed for acoustics, this was not clear. Yeah. And the issue really is with this convergence of measures on the boundary. And this is what we are tackling. So what is the problem here? In general, weak convergence is very good for most purposes, but it's difficult if you want to fix a class of admissible domains over which you minimize, because if you V convergence can change the type of measure that you look at. So suppose, for instance, what was done in a more classical context, that people would look at Lipschitz domains. On Lipschitz domains, it's typical that you would like to take reasonable n-1 dimensional Hausdorff measure on the boundary, right? And then this is what you work with. You can do you can prove well-postness, you can do everything, and then you go to convergence, and you observe that if you have bad luck, then the mu n's, who are all Hausdorff measures on the Lipschitz boundaries, converge to a target measure weakly, mu, which is also some good measure, but it's no longer a Hausdorff measure. Yeah. So the target domain may still be a Lipschitz domain, but the measure on the boundary that you observe in a limit is no longer a Hausdorff measure. So it will somehow be different. It could be equivalent. Yeah. So you need to give some more freedom to this measure. Otherwise, it's difficult to prove compactness. And this is the reason why the existence of optimal shapes for problems involving Robin boundary conditions were not known in, or was not known in the classical Lipschitz framework. And our friends in a collaboration with a group, they observed this effect or analyzed this effect a little bit more in connection with acoustics problems. And the outcome of this paper here was that, well, you can still find some limit of an optimizing sequence, but this limit is not going to be a minimum, not because it's going to be an infimum, yeah, because it's outside the class, so to speak. Yeah? So it's not going to produce a minimum of the energy on that particular fixed class. And now our suggestion was quite simple, actually, quite naive. If we make the class a bit broader, if we make the class of admissible shapes larger than just Lipschitz shapes with Hausdorff measure on the boundary, maybe then we have good compactness properties. And indeed, this worked well. So we wrote a paper which came out last year, where we looked at quite large classes of admissible domains from which we could recruit to try to find an optimal one. And these were allowed to have boundaries that could be fractal, that could be quite bad, actually. And this was done here. And this setup actually it's possible to prove the existence of optimal shapes that minimize the energy. So this is what we target now. Let's talk about how this can be done. If it's too boring, please speed me up, right? If we talk about strange boundaries or about boundaries in general and integrals over boundaries, then we must think about how to take traces of like Sobolev functions and so on the boundary. Let me go through this quickly. This is quite classical, I guess. So the boundary will be a closed subset of Rn, of course, so it has empty interior, so it's not so clear how to restrict, say, a Sobolev function to such set. So we need to define suitable traces. But of course, what we can always do, we can, for any locally integrable function, consider its pointwise redefinition, as you would do in Lebesgue's theorem, right? And then Lebesgue's theorem tells you this converges almost everywhere. But actually, if your function is from a Sobolev space, then the situation is much better. It does not just converge almost everywhere, but quasi everywhere in terms of W12 capacity, which can see much smaller sets. Yeah? So convergence behavior for Sobolev functions is quite good, quite acceptable. We could hope to work with that. So we have a limit except on a set which has so-called zero capacity, so it's a quite small set. And if now we want to do some reasonable analysis on the boundary, we could try to hope that if we take a measure which is sufficiently diffuse, that it just doesn't charge the set of zero capacity. And this is what people do. So one easy and pragmatic condition to see the measure is diffuse enough is to say that we look at the measure mu with support gamma, which is locally upper deregular, which means that if you look at the measure of a ball with the center in gamma and the radius, like let's say smaller than 1, then this ball can always be estimated, the volume of this ball can always be estimated from above by a fixed constant CD times r to the power d. Yeah, and d is like a dimensional parameter. If this is the case, it's not difficult to see that the Hausdorff dimension of gamma must be greater or equal d. So gamma cannot be too concentrated. Yeah. So you cannot take d greater 0 if your measure is a point mass measure, if it's too concentrated. And then if d is large enough, then mu is diffuse enough to have this pointwise redefinition of a Sobolev function being a reasonable mu equivalence class. Yeah, so this is quite classical, but we need it, so I repeat. Now, we can even say more. We cannot just talk about being a reasonable equivalence class. We can also talk about moments, so integrability conditions. So let's assume that D is a parameter which is less or equal n, and also it's greater than n minus 2, which is definitely good enough if we want to have a boundary between with dimension between n minus 1 and n. Right? So a thick boundary would have dimension between n minus 1 and n. We could actually do a little bit more. We could even spread a little bit of singular mass on an n minus 1 dimensional boundary. It's not forbidden. If it's satisfied and mu is a finite measure and upper D regular with this particular D, then this pointwise redefinition we had on the board defines a nice bounded linear operator from W12 on Rn to the space L2 gamma mu. And the norm depends only on these quantities n, d, cd, and mu of gamma. And this operator is also compact if gamma is compact and so on. And now what we do is we view this operator as a map from the space W12 onto its image space. So the image space is some vector space, right? And in this work that I'm talking about here, we don't even care what it looks like. Yeah, we just say we want to have minimal assumptions on the measure. If we don't impose further assumptions on the measure, we may not exactly know what the norm in the space looks like in a constructive way, but we don't care. Yeah? We endow it with the natural quotient space norm, and then we see this trace operator as a linear contraction. We can, by Stone-Weierstrass, we also see this trace space is then dense in L2 gamma mu. So trace gamma of W12 is a space on gamma, and it's dense in L2. If one invests a little bit more, then one can, so this is for instance done in the works by Johnson, Wallin, and Johnson in the 90s. If one invests, if one says, well, the measure should not be just bounded from above for each and every bulb by CD times R to the power D, but also from below with a different constant, then one is in a situation of a so-called D measure. Then one can identify this guy as a typical Bezoff space on gamma. And if one doesn't insist on this, but introduces some what is called refined scaling conditions or refined doubling conditions, then this still works. Yeah, but we don't want to have complicated conditions in this work on the measure. So also this space is not used explicitly. But nothing would change if you invest more. You could still do the entire concept, and you would have constructive information. Yeah. Okay, so now this is just about the trace and the boundary, but we also need to have some control about the domain itself. And what we will assume is that, for instance, to prove well-postness and to have nice access to traces on the boundary, that omega is a W12 extension domain, which means if I look at the Massia type Sobolev space W12 on omega, then I can always find an extension of any function to Sobolev function in W12 Rn, and this extension operator is nice. Yeah, this is done by a nice extension operator, bounded linear extension operator. Suppose this is the case, then we can combine this extension operator with the trace operator to the boundary and find that there is a nice operator which takes a function, which defines us nicely the trace of a function in W12 omega on gamma. If gamma, for instance, is a portion of the boundary partial omega, but it could also be a more general subset inside the closure of omega. Doesn't matter. Yeah? That there are no problems with consistency was proved by Wallin in the 90s by sort of pointwise redefinition methods and using Bessel kernel and so on. And then again by Wiegert in 2009 from the Ulm school using so-called relative capacities. No? So there's no issue. One can define this nicely. This we use to prove well-postness. So this tells us we can talk about the trace, which occurs in the Robin condition, but we also need to know about normal derivative, which occurs in the Robin condition, right? So we need to get ourselves a normal derivative. And how can we do that? We can say somehow, in a somehow synthetic way, that the W12 function is in some sort of domain of the Laplacian, defined in a suitable way. It's maybe not so important right now. If something holds, And for all these people from this domain, we can then introduce a normal derivative, abstract normal derivative in some sort of distributional fashion by just abusing Gauss-Green formula. Yeah? So we take Gauss-Green formula, the energy part, the Laplacian part, and using these two, we define a dual pairing on the boundary, and running through all test functions, this defines a nice element of the dual space, which is our generalized normal derivative. Here, h gamma omega psi is just, I mean, I put here the harmonic extension from the boundary to the inside, but actually you can take any extension. It's not very. So we get also a well-defined generalized normal derivative. Also, this is not so new. For simplicity, I will now not talk about the mixed boundary value problem because it's just too much notation. I will reduce the discussion in this talk to the Robin boundary problem, yeah? Because the Robin condition is what we are interested in. So let's assume we have a nice W12 Sobolev, W12 extension domain. We have a subset of the closure of this domain. We have a parameter alpha greater or equal 0, a non-negative function gamma, which is also bounded. And we have some inhomogeneity f in L2 and some boundary data phi from the trace space. Then we can look at this problem here. Alpha minus Laplacian of u should be f in omega minus gamma. And the Robin condition, partial u, partial n gamma. So this is the normal derivative plus gamma, with gamma trace of u should be phi on capital gamma. And we can make this rigorous by simply saying u should be a weak solution, or u is a weak solution if it solves this integral identity. So this is just variational formulation of this boundary value problem, right? So this variational formulation we will work with. So this is maybe a little bit boring. So let me go through this quickly. If we are on a W1 extension domain, D is reasonable in a reasonable range, as we just discussed. We use non-zero finite Borel measure, locally upper D regular, and so on. And all the alpha parameters are as before. Then, just to make life easy in the talk, if alpha is greater 0, then there exists a unique weak solution to this thing, right? So it's just well-postness. Well-postness is fine. We can still work with alpha 0 if gamma is strictly positive and so on. But this is not the official statement. It's just its simplified statement for the talk. No? Under reasonable conditions, it's just you can use Lax-Milgram or something like that. You see coercivity, all is fine, and you get a unique weak solution. Now we're interested in the associated energy functional. And the associated energy functional for this problem is this one. So let me indicate omega and mu, because omega is fixed, mu is fixed, and they will vary later on. And also the parameters alpha and gamma are fixed. And then if we insert a function, then this should be the typical Dirichlet integral plus a little bit of the L2 scalar product, or L2 norm squared, plus the boundary term. So this is the L2 norm, in the L2 space, or the square of the L2 norm in the L2 space on gamma with weight little gamma times measure mu. All right, so that's the energy function. And then if one exploits Lax-Milgram and so on, one can see that, of course, if the function solves the variational formulation uniquely if and only if it minimizes this energy functional, right? So this is quite standard, but that's our formulation. Now it becomes a bit more spicy, perhaps. We talk about convergence and stability. Now, in order to find an optimal domain, or an optimal shape, first we need to be able to discuss about convergence of shapes. Yeah, and in shape optimization, there are typical modes of convergence that people use. One is convergence in terms of characteristic functions. So they say a sequence of domains omega n converges to domain omega in the sense of characteristic functions. If just the characteristic functions, so the indicator functions of these guys, they converge in LP locally for all reasonable P. Yeah. Then there's another mode of convergence, which is convergence in Hausdorff sense. So first of all, let's look at two closed subsets of Rn, K1 and K2. Then the Hausdorff distance between these two sets is given by an infimum of epsilon greater 0, so that K1 is contained in the epsilon parallel set of K2, and K2 is contained in the epsilon parallel set of K1. I mean, maybe I make a picture. So you want to have some sort of, this is maybe some parallel set of 1, and one of these guys should be contained in this parallel set. So if this is K1, say this is K2, we want K2 to be contained in the parallel set of K1, epsilon parallel set of K1. So this is epsilon, and and we ask for the minimal epsilon that this happens, and we ask this question in a symmetric way. Yeah. So we want them to be close in this sense, and then once we have clarified this notion for closed sets, we can ask it how can we give a meaning to that for open sets. And for open sets, it's customary that for these type of problems, we could choose a bounded domain, a huge domain that contains everything, so a confinement domain, and then simply look at the closure of the confinement minus the respective open set. So this gives a closed set, that gives a closed set, and we can then hope that these two closed sets converge to 0 in this metric. Yeah? So this is very typical in this very typical way to measure distance between two different domains in this business of shape optimization. Yeah? So a priori is defined for closed sets. We choose a bounded confinement containing omega n and omega, and we say omega n converges to omega in the Hausdorff sense if these closed sets converge. So we look at, roughly speaking, the complements in the confinement. Now, there's a first theorem on the convergence of the energy forms. Yeah, so if we master the convergence of the energy forms, we can say more. We can step to the convergence of resolvents, of spectrum, and so on, right? By typical theorems. So what we want to prove is that these energy forms, these are the energies we just had on the board. Now I look at them for the approximating domains with omega m, with boundary measures mu m, and I want them to converge to the target domain omega with boundary measure mu. And what I would like to see is that they converge in the sense of Moscow, which implies also gamma convergence and so on, right? And implies nice spectral convergence. So if n is greater than or equal to, and D is a bounded Lipschitz domain, so the confinement we assume to be Lipschitz, the coefficients alpha and gamma are reasonable, and epsilon is some parameter greater 0. So I will talk about some specific domains here. I will give the definition on the next slide. So we will be a bit more specific. We will not just talk about W12 extension domains, but more parameterized, strictly parameterized family of domains. And then we take D as before, and we assume that omega n is a sequence of so-called epsilon infinity domains contained in D. Yeah, so a specific type of domain, hopefully W12 domains, otherwise we would exclude. And mu n is a sequence of non-zero Borel measures on sets gamma n, which are the supports of these measures and contained in the closures of these domains omega n. All locally upper regular with the same constant. So remember, there was upper regularity condition was CD times r to the power d, and we want this CD to be the same for all these measures. Yeah? So uniform conditions here. Then, if the domains converge in the Hausdorff sense and in the sense of characteristic functions, and we have weak convergence of the measures, then we can say that also the target domain, which we don't know so far, is going to be an epsilon infinity domain with the same epsilon. It's going to be contained in D, and mu is and the target measure, the limit measure, is going to be a non-zero Borel measure locally upper D regular with the same constant CD, and it's this should be gamma. Sorry, this should be gamma. This should be sub mu, and this should be omega bar. So please mentally erase the m's here. So everything is as before, also for the target. And moreover, we have the convergence of these energy forms in the Moscow sense. Yeah? So this is what it does here. Let me first clarify this notion of epsilon infinity domain, which is relatively classical by now. It's from the 70s, Matthew Saraf, Spacele, so like the Finnish school did quite a lot. extension and restriction extension operators with uniform constants, uniform operator bounds were established by Jones and Rogers.
Yeah,
so what?
Yes,
Yes,
a question in the previous slide.
Yes.
Sorry for continuing. So you require that these domains converge both in the Hausdorff sense and in the sense of characteristic function.
That's correct.
Is there usually a relation between these two kinds of convergence, or is not really known?
I'm not so sure because I mean I don't think there is a, let me say, I don't think there's an obvious relation that we can easily exploit to simplify this assumption. Yeah? So I think there's certainly room to optimize also the classical theory, but no one knows. So if we go to Lipschitz setup, they would assume something very similar. You know? Here the point is, I can tell for the energy, we just use characteristic function convergence and convergence of the of these measures. This is what we use to have the convergence of the energy function. But Hausdorff convergence ensures us that the limit domain is going to be an epsilon infinity domain, which is in particular a W12 extension domain. So we get well-postness. So this Hausdorff sense convergence guarantees us that the target domain is of the same type.
Is the relation now, say, for more regular domains? I suppose you have C1 domains or smooth domains. Are they the same thing?
Yeah, if you have Lipschitz domains satisfying a uniform cone condition, it's the same.
Okay.
So that's maybe, and here we have uniformity also in this epsilon.
Thanks.
So so let's take n greater equal 2, epsilon greater 0, so uniform parameter. A bounded domain in Rn is called a, so we only talk about bounded domains here because that's what we need for practice. It's an epsilon infinity uniform domain. For all 2 points in the domain, you can find a curve going from one of these points to the other. And along this curve, we can still put a little, well, people say banana or cigar of a certain parameterization, and this entire banana or cigar is still in the domain. Yeah. So this is what these. I will not read these conditions. It's just you can put a banana or cigar, which is parameterized, and it's still going to be in that domain. Yeah? And it's very well known from these works here that epsilon infinity domains are very, very nice W12 extension domains in the sense that extension operators will have a norm depending only on n and maybe your Sobolev space P and K and epsilon, and that's it. Yeah, so they will not depend on anything else but these belongings. And then we proved a theorem which says actually, and it's funny, the proof of this goes back to all the ideas of Fréchet. Fréchet has convergence of curves somehow, and this is super cool to use to prove the stability of this banana condition. Yeah? And then we see that if a sequence of such epsilon infinity domains contained in a confinement D has that any sequence, of such epsilon infinity domains contained in the confinement D has a subsequence which converges to an epsilon infinity domain in a Hausdorff sense. No? This is just maybe a truncated statement. If you go in there with the convergence sequence, then of course you also get that the limit is epsilon infinity and contained. Yeah? So this gives us, this is how this Hausdorff convergence comes in. It gives us the stability of this type of domain. Okay, now for boundary integrals, also we want to have this, so that we want to have convergence of these boundary integrals because they are part of our energy functional, right? But this is less difficult because we can just shamelessly exploit the weak convergence. We can use some nice smooth functions to approximate this inside W12D, so it's not so drastic to prove this. I will just tell the statement quickly. So if we have a sequence of Borel measures as before in the theorem, and they converge to some measure mu weakly, then local upper regularity is preserved, containment of support in the bar is conserved and is preserved. And if we take a weakly convergent sequence in this Sobolev space on the confinement, then we have this limit relation for the integrals on these gamma n and gamma with respect to mu n and mu. So we had this theorem on Moscow convergence, and now we can, this is just a convergence theorem, and now we can upgrade a little bit and say, well, actually we have a compactness result. Yeah, so we can take a sequence or maybe a pool of domains. Sorry, this is first of all for functions, sorry. So let um and u be the unique weak solutions with zero boundary data on omega m, with some sort of inhomogeneity gm, which can vary, and an omega with some inhomogeneity g, and assume that the inhomogeneities converge weakly in the L2 space on the confinement. Then we can find as a sequence, we can single out the sequence, and we can find a function such that the restriction of that function to the target domain is going to be u, and we get nice convergence with suitable truncations in L2D, and we get nice convergence in weakly in W2D, and we get convergence of the energy functionals, yeah, with these particular solutions. So this is sort of basic compactness result here. Under the hypothesis of this theorem upstairs, right? So that we have convergence of the domains in this specific ways. I didn't repeat it, yeah. So this is consequence of this Moscow convergence. So we assume convergence in terms of characteristic functions, Hausdorff sense, and reconvergence of measures. And also, if you restrict to W1 to omega, we have this sort of stronger convergence. So once we have convergence of the domains, compactness for sequences of solutions, so to speak, is no issue. Yeah. So the compactness issue now is really reduced to the side of the domains somehow. So if we have this entire setup, then we can also make conclusions. Let me just mention this briefly about spectrum. So actually, we cannot just get Moscow convergence, but we can upgrade it. Moscow convergence would correspond to some sort of, in this case, generalized strong resolvent convergence. If we upgrade a tiny little bit, we can even get some sort of generalized norm-resolvent convergence, which means we have, in quotation marks, direct convergence of eigenvalues and eigenfunctions. You know? Of course, one has to choose cool sequences and so on. And this is very much related to work of these people. And they have a paper where they actually, I will tell later on, they do not use any uniformity. They work on Lipschitz domain, but Lipschitz domains, it's quite similar. They use an import from theory of BV functions. And what they can do very nice, up to this point, they can do more or less the same, except that they don't use more general boundaries, they use Lipschitz boundaries. On the other hand, they do not use uniform Lipschitz boundaries. Yeah? And we use wild boundaries, but uniform by epsilon in a sense. But they cannot do compactness. Yeah, so that's up to here. I would say we do something that is somehow related. There's also some completely other approach to stability of solutions to boundary value problems on domains using an old approach by Masia, where tracing is organized completely differently. And this was investigated quite a lot by Dancer, Danas, and other people. But what happens there is they could prove that if you use this type of approach by Masia, then you can have sequences of converging domains and boundary value problems on these convergent domains. But in the target domain, you may get a different boundary value problem. Yeah? So they can change. And this will not happen for what we do. Now we go to something that was not clear, that maybe it's debated here, the compactness and the existence of optimal shapes. So what we do, we need to prescribe some sort of class of optimal domains. This looks horrible. Let me try to bring it down to earth somehow. So what we do, we look at triples, and this, it can be reduced a little bit, but let's look at triples: omega, nu, and mu. Omega is a nice epsilon infinity domain, which is contained in a confinement D and contains some smaller open set d omega, which just, I mean, there's a pragmatic way to say they should not collapse. Yeah, they should still contain something. Then we have some condition for upper regularity for the measure on the boundary, as before. Local upper regularity for the measure mu in the boundary, but we introduce also another measure, mu. And this measure is, oh, sorry, mu does not necessarily have to be on the boundary. So this could typically be part of the boundary or the entire boundary, but it could also just be another set which is in the closure of omega. Then there's another measure which is just a tool for us, just a topological tool. This is now a measure on the boundary with support boundary, and it satisfies a lower regularity condition, but it's somehow a weaker regularity condition in the sense that we look at close balls. Yeah, this is just number 2 is just a tool for us. Number 2 is just a tool for us, and it has bounded total mass uniformly bounded by such constant. If all these parameters are fixed, so these two domains, the confinement, the domain which is contained, the epsilon for the epsilon infinity condition, scaling exponent for the measure nu, and constant for the measure nu, total mass for the measure nu, and the exponent and the constant for the measure mu, then we say this triple is inside this parameterized class UAD, U admissible. Now, what happens is that now one can prove compactness. This class is compact in the sense of convergence in the Hausdorff sense, in the sense of characteristic functions convergence, in the sense of convergence of compacts, which is yet another typical type of convergence employed also in classical approaches to shape optimization. Yeah. And also in the sense of weak convergence of the measures nu and also the measures mu. So the measures nu, perhaps one can call boundary volumes because they just talk about the topological structure of the boundary, and the trace volumes mu are the measures we are really interested in our PDEs. And then also we have some auxiliary statement which says that basically the convergence of the measures already determines more or less everything. So let me skip number 2 perhaps. Yeah. And this actually, this was a bit of work to prove, not too much, but yes, maybe a bit more serious. As I said, these boundary volumes nu are just used as a topological tool, because what can happen if you have such convergence of domains in various ways, you need something that prevents bleeding. So you have a boundary and still there could be some in-bleeding into the domain or out-bleeding, I cannot quite remember. Yeah, so the domain could make some like intestinal structure. And to prevent this, we use these measures nu. This is basically behind it. Now, what we can do if we fix such parameters and we look at the sequence in such parameterized class, then we can really have observe compactness. We can single out a subsequence, and we can find a domain such that we have convergence to that domain according to the last theorem, and also we have convergence of the energy functionals in the Moscow and therefore also in the gamma sense. And then the corresponding solutions, the solvent operators, spectral projectors, and so on, converge as stated before. Yeah? So once we have settled this compactness issue for the domains, by what we did before, it gets inherited to the solutions and to the energy forms. Yes, please.
So sequence logically logical differences.
Let me think. I can't quite. I have to look up again. I must say, I can't quite remember that exactly. There's a catalog of things which can happen and which are forbidden to happen. Yeah. So what I can say, they don't collapse. They don't split into two. Yeah. They don't collapse. No. I think this is excluded by using this DO inside. This DO inside. So we cannot completely collapse to a point. This is prevented. But I agree. So that there's a lot of things to talk about. But so we will be in epsilon infinity domain, and DO will be contained. We will not split in two domains. I think this is what I can say for sure. And otherwise, we have to talk a bit more. All right. So there's a special case. A special case would be where we choose is mu and mu to be the same. This is somehow some sort of a simplified special case, and where gamma is supposed to be the boundary of omega. So this is what we need for our practical problem. It's an easier version of what was stated before. We fix all the conditions. Then we can make sure we can find actually an optimal element of this class. So that's a slight cosmetics because we use mu equal mu here. But apart from the slight cosmetics, it's exactly what we did in the last theorem. So we can find an optimal class such that the energy, we can find an optimal domain with these measures. Now mu is the same as mu. And if we apply the energy form here to the unique weak solution on this optimal domain, then this energy is exactly the minimum over all the possible energies on that class, of the solutions on that class, on members of that class. So this is existence of optimal shape in that sense. So we did not only find optimal omega, but also optimal mu in this larger class. But mu, as you see, so this is still in this domain, mu can be quite wild. Mu can be, so support of mu can be have any dimension between certain bounds. Practically, we could cover anything between n and n-1. So we made the class very huge, and we observed compactness here. So let me mention, so this was maybe our main result. Let me mention how this can be compared to other results. There are other results for existence of optimal shapes for non-Lipschitz domains with Robin problems. These are due to these authors, and what they do, they use a countably rectifiable boundary, which means you're basically n-1 dimensional. Yeah? And they do not look exactly at the same energy functionals as we did. What they do is they go into a theory of BV functions, and they do some sort of relaxation of the energy functional. So they change the energy functional, they change the problem in order to be able to observe compactness. We do something else. We don't change the energy functional, but we make the class of possible shapes very huge. Yeah? What they do not need is any uniform control. So we have a uniform control by this uniform epsilon and by this constant CD, CS. That's what they don't need. But of course, they are bound to this n-1 dimensional thing, and they change the functional. What we do is we use exactly the given energy functional, and we can also discuss boundaries of any Hausdorff dimension in that range, basically. But we have to say there's a certain uniformity encoded in this uniform choice of epsilon infinity domains. Yeah? So this is maybe how one can roughly compare these ideas. All right. So what we are currently doing is, well, this was just, what I presented was just for Robin problem in a very easy fashion. We also did it for a mixed boundary value problem for this Helmholtz equation. We are now doing it for Robin problem for the Westerveld equation, which is a nonlinear PDE that which describes the propagation of ultrasound waves, yeah? Which is interesting, of course, for diagnostics and so on. Another item that we can say we will do soon is here we just proved Moscow convergence or something like this, or normal solvent convergence, and actually one can make a relatively quick upgrade with precise error bounds for the eigenvalues and so on. Yeah? We didn't do it here because for optimization it doesn't play any role, but it's not so difficult to do it. Something else is point 3 is maybe more essential. Now we just proved that in this large class optimizers do exist, but we have no idea what they look like, right? So the next step would be how can we approach some sort of algorithm or whatever to perhaps find an optimizer. This is a larger question, and we believe we can do it. But this is hard work. It's going to be hard work this year. We believe we can do it with deformations by quasi-conformal maps, because then one can control nicely how the dimension of the boundary pieces change and so on. This looks quite promising. I hope it will work out. And in the long run, we would be very, very happy. I mean, this is the long goal of this, or one of the long goals of this program, to perhaps prove some sort of folkloric conjecture, which was announced in the beginning, that for some problems, for instance, in acoustics, the optimal design, I mean, if you take an idealized problem with many, many different frequencies, then maybe the optimally designed shape cannot be smooth, but will rather be fractal, to give an obstacle to each wavelength, so to speak. This is what it's the folklore belief, but the dream would be to make this like rigorous in some sense. Thank you very much.
Thank you very much. Virtual clapping. So are there any questions either from the live audience or virtual audience? So Alexei.
Yeah, so for the optimal domain resonance, you wrote that it's got a Hausdorff dimension boundary of this domain strictly less than D. Right?
Strictly less than n, right?
Strictly less than n, where n is the dimensional ambience.
Right.
So why is this? Is this because
at some point, I don't know how essential this is, but at some point for us it was convenient to use a very tiny dimensional gap in an argument, because so we have at some point we have a sort of topological argument where it is beneficial if this parameter d is strictly smaller than n. I do not believe this is absolutely necessary. Yeah. So
in your class you assume that all the boundaries have
yes. So we we assume this. Let me see, where's this definition? It's here perhaps. So it's this inequality which we want. Yeah. If we have this inequality, it's quite helpful in a proof. Yeah. I think you can lower it probably. So I don't think this is the optimal argument, but for pragmatic reason, it went quickly.
Other questions?
Is there anything known at all, and we have talked about it here, is there anything known at all about unbounded domains?
I cannot answer. I don't know. I think, yeah.
Even with a bounded boundary, so the exterior of bounded domains.
I suppose there is classical results, and then one could try to work along classical results. I do not think for us it's super crucial to have bounded domains. Yeah? But where I would start to look at is like these classical works, Enro, Pierre, and look up what they did for like domains with Lipschitz boundary. I think there may be also cool results for unbounded domains. And if they have these results, it's very probable we can do this program also for these results. But I don't know this. I didn't look into that.
Further questions? Perhaps from the virtual audience or from the live audience? I don't see any kinds of questions.
So when I was reading the proof of the Bosco convergence trend, and it seemed like the uniform boundedness of this extension operator
Yes.
Plays a really crucial role.
Yes.
So would the theorem work if you instead say assume that these domains, the sequence of domains omega n, instead of assuming the epsilon infinity uniform domains, could you assume that the extension operators are bounded uniformly?
Yes, I guess so. Yeah.
Okay.
I guess
that
so.
would work.
That will do it.
Okay.
So perhaps I'll just ask kind of curiosity at the end. So I know of sufficient conditions for W12 for a domain to admit W12 extension. And the question is, how horrible can a domain with such a property be?
Oh, well, I mean, the classical standard example which you can cover is for suitable epsilon are all types of Koch curves, for instance, that you can. And this means you can already exhaust all the possible dimensionalities of the boundary between n-1 and n.
Thanks. There are no further questions. Let's thank for the very nice book. Okay, you can stop there.